Thanks everybody for joining us today. So yeah, like Zoe mentioned, a lot of my research is focused on trying to basically understand the capabilities and limitations of quantum computer. Most of the time I approach these kind of questions from a theoretical perspective, trying to provide mathematical tools and mathematical proofs that aim to understand, what's the regime in which you can have quantum advantage, both from the perspective of classical simulability, so where does the kind of boundary between quantum advantage and classical things that can be classically simulated lies, but also trying to understand how and characterize errors and how those errors affect quantum algorithms. So for the talk today, this is going to be a more practically minded applications of kind of related to these questions. So I'll be talking about a series of experimental demonstrations on continuous ion trap devices that we've done very recently, both in the context of simulating physics, so noisy quantum simulations, but also leading into quantum error-corrected computations. And we're kind of explore a little bit how some of the ideas from suppressing noise in current devices kind of can be taken forward into a regime where you start performing kind of quantum error-corrected computations. So just to give you an overview, Quantinuum is like a pure play sort of quantum computing company, and amongst other things we have ion trap based hardware. So this is based on quantum charge coupled device architectures. So these are two of the architectures that are currently available online. You can access it, you can sort of play with it and run your own experiments. So the H12 has 20 qubits, it's a linear trap, has kind of pretty decent fidelities of hitting 3 nines on the 2 qubits and 4 nines on the single qubit. And more recently, I think early last year, we introduced a 56 qubit device. This one has a race trap architecture, and you can see here that the 2 qubit gate fidelities, at least the ones benchmarked in the experiments I'll be talking about, have actually improved with this new device. So for the H2, just to give you a kind of overview of how the quantum device works, it has this kind of racetrack shape, and you have 4 gate zones. So the blue regions in the middle are regions where where gate operations are performed, and ions get shuttled around this racetrack in order to move ions around and bring them back to perform gates between different qubits. So the ion species is the ytterbium, and that is sympathetically called like the beryllium species. And so so the native interactions I have here, the 2 qubit gates that parameterized by some angle theta generated by ZZ, but more recently you can also access a universal SU4 entanglement gates. And the 1 qubit gates are in the kind of X and Y plane. So you can look up more details about the H2 and architecture and all of the kind of benchmarking for this device in this paper. In the archive, I put the archive number in the corner over there. I usually use archive numbers just so that it's accessible to everybody. So in most places I will have links like that. Maybe something that people are not aware of, we actually publicize, so our randomized benchmarking data and all of the kind of quantum volume benchmark. They're all publicly available on GitHub. So there's a lot of data going around, and these are very highly benchmarked devices. And maybe another thing that people might not be aware of, Quantinuum devices get periodically upgraded. So you will see that maybe when a new device gets released, it has certain error rates and certain fidelities. But over the course of time, we perform upgrades that improve the fidelity. So that's why we ended up with a 9.39, 99.94 fidelity, 2-qubit fidelities for the H2 through a series of continuous improvements. Okay, so now that I've kind of given you an idea of what Quantinuum devices look like, so the first part of this talk is going to be focused on a simulation of dynamical physics, basically, so a dynamical evolution that's trying to simulate certain observables of a Hamiltonian that's an effective description of quantum magnetism. So this was a large collaboration that included people from EPFL here. Manuel Rudolph from Zoe Holmes' group was involved in some of the classical simulations. So the kind of big overview of this work is that we were able to perform, because of the high fidelity of the device, we were able to perform long-time dynamical evolution in a regime where performing that with various classical methods, they start breaking down. You no longer have convergence in those regimes. So the kind of overview is that we sort of started with an Ising model on a torus, and perform a digitized dynamical evolution. And you have here sort of a schematic of how one particular Trotter step looks like. And we look at physical phenomena that you can observe by measuring this time-evolved state. And you can observe that with time you have these kind of pre-thermal statistics emerging as you kind of increase the dynamics of, increase the number of the time evolution. So this is a 56-qubit device. So we're looking at a 7x8 lattice with periodic boundary conditions. So it's a transverse field Ising model on 2D, and we start off with an input state that kind of controls the energy density of the system, and you have a time evolution that gets approximated in this case by the second order Trotter, so the digitized second order Trotter evolution, and that kind of, if you're expanding out the Trotter steps, they will look like this. And so now, one of the things that happens is that when you start to digitizing, so there have been a lot of quantum analog simulations of quantum dynamics, but this is a simulation done on a universal quantum computer. So when you try to digitize the evolution, you have an effective Hamiltonian that you are simulating. You're not simulating a continuous time, but you have a so-called kind of Fouquet effective Hamiltonian that you apply to your input state that you evolve. So in particular, there is this kind of phenomena that as you decrease the digitization error, so the Trotter step, the DT, you start observing behavior that looks very much like, that is very much stable and looks like what you would have in a thermal limit. So there's been a series of works that show that, with decreasing digitization error, you experience an exponentially long window or pre-thermal behavior that scales exponentially in the inverse of this DT trotter step. So here is an example where the observable that we look at is the average squared total magnetization across the entire lattice, and you can see that as you sort of in a certain regime of trotter step, you start observing these pre-thermal plateau behavior. So so this kind of tells you a bit about how to pick parameters in such a way that your effective Hamiltonian that you implement starts to simulate the physics of the Ising model on that system. So this is a kind of pre-thermal phase diagram. So on the y-axis you have the initial energy density. So this is the energy density of the input state that you have. So the angle of that state, or rather the difference between to the mean field value. And on the y-axis you kind sort of swipe over a range of parameters for the coupling coefficients, for the spin coupling coefficients, and the transverse field coefficient. So this is a sort of integrated, so averaged out over some series of trotter steps, I think 30, and it's for a small 4x4 system where we can have, you can do it numerically on your laptop, basically. So these are the kind of pick two different quenches, and by quench I mean the initial input state that you start with, and also the parameters for the H and J. Yes?
Why do you say different temperature? You said coherent. These are just qubit states. You don't.
Yeah. So it's just that the energy density in these systems plays a role similar to. It's not exactly the same. It's similar to temperature. So that when you're close. So here you will be closer to the mean field value. So call it a low temperature quench. And this is a regime, the low temperature quench is a regime that is classically simulable because this input state also controls the amount of correlation built up through your circuit. So you end up with low entanglement entropy, and you can handle this parameter regime. You can handle that with matrix product states. Whereas a higher kind of the energy density that becomes more difficult. Okay, so these are kind of like the parameter regimes that we pick for our simulations, and so in order to kind of run it on continuous devices, you do the usual thing where you compile your trotter step into the native gates. And in this case, we do have a native gates that are ZZ rotation, so you end up with four layers because you're going two of them in the x-axis and the other two in the y-axis on the lattice. So in order to to actually run this kind of simulations without any, you will be kind of affected by noise in the device, especially as we are targeting long time dynamics. So in order to combat the kind of effect of noise, we combine a series of error mitigation strategies. So the first two over there, randomized compiling and dynamical decoupling, are targeting coherent errors. So errors that are unitary and they occur as a result of a magnetic field that's in the trap, and it mostly occurs when you're trying to shuttle ions around the racetrack. And the zero noise extrapolation aims to reduce the effect on the observable of those error sources that are stochastic. We also have leakage because we have ions, so they can leak into a higher computational, outside of the computational state. So we also do some leakage detection at the end. And so let me just move on and tell you a little bit about how these error suppression mechanisms work. So randomized compiling, also known through various other names like Pauli-Turling and Pauli-frame randomization, is the idea that you can tailor a general noise model that affects, say, a particular gate. In this example, is a C0 gate, by applying random single Pauli operators. That has the effect of converting a noise model into a probabilistic mixture of Pauli errors. So it becomes, so if you have a unitary error, that becomes a incoherent stochastic error. And so in our particular case, we're introducing random Pauli operators onto the ZZ rotation, and in this case you get a plus or minus theta, because you kind of propagate, as you propagate the Paulis through, then that gets a flip in the sign. So the idea is that if you have no noise, then these two will be the same, but when noise is present, the role of these randomly inserted Pauli operators is that it will kind of take care of the coherent memory error and other coherent errors in the gate. So the next step is to kind of try to eliminate some of that probabilistic sources of errors. And for this, there's a lot of techniques that try to mitigate errors in computing expectation values of observables, and so they all kind of have a very broad kind of framework that you can fit most of those methods in. So we start off with some observable and a circuit, and you want to produce, and that circuit is affected by stochastic noise, and you want to produce an estimator for that observable that reduces the bias that noise introduces. So generally speaking, you start off with some characterization of your noise, and you do that by running some modified circuits of the one that you started with, and then based off your knowledge of how noise affects the device or the circuits, you fit that to a functional model, and with classical processing, you produce a mitigated estimator. Generally, this has the effect of introducing variance, so you would need to run more shots in order to get the same precision for your observable. So in this case, we're doing zero noise extrapolation, and the idea is to kind of artificially increase the noise levels, and then perform an exponential, and in other cases, like a polynomial fit to a zero level of noise. There's various ways of how you artificially increase noise levels, many kind of approaches, but in this particular case, we're doing that based off the very thorough characterization of the gate errors in the ZZ interaction. So here you see, like, the probability for getting a particular Pauli error on the 2 qubits. So you get this histogram, and the 2 different colors represent 2 experiments taken at different times. So the error model is quite stable in time and across the sort of duration of the experiment. So once you have that error model, then you can amplify the error probabilities based off of that error model. And that's done by inserting Pauli operators that are sampled accordingly, according to a scaled up version of these error probabilities. And after that, you extrapolate to a zero level noise with an exponential fit. And finally, we also look at handling leakage, and the way that was done was through sort of detecting whether a qubit has leaked at the end of the computation, and you can do that with a kind of ancilla qubit that, in the absence of, if the bottom qubit did not leak, then the top qubit you would just get a 1 on measuring that. In the absence of, if the qubit is leaked, none of the operations get to be applied, and in that case, you will see a 1. Okay, so once you've detected some number of leakage events, then what you can do, you can post-select whenever you see that one of your qubits has leaked, but that has an overhead. Like, you can't do that in a scalable way because you will need to post-select an exponential number of shots. So one of the techniques introduced here is to try to fit, sort of have a heuristic fit that you get an estimator for the observable by looking at a histogram of the number of leaked events that have occurred, and try to fit that through to what it would be like if you had no leakage events. This is what would happen if you wanted to scale to longer time simulations. In the case that we had, there's the idea is that in the latter regime, with the latter option, you get not so much overhead in terms of number of samples, so you reduce that variance. So these are kind of the results that we obtain on the H2 system. So you have a reference, a matrix product. So this is for the low temperature quench. So this is the easy simulation that you can run using matrix product states. So you see the blue, the solid blue, not blue, purple. Yes, purple, solid purple. That's an extrapolated matrix product state value. And the purple dots are the results that you get after you perform all of these combined error mitigation strategies. And the green ones show you the amplified the observable when you amplify the errors. Okay, so the idea of performing this is that it gives you a benchmark that your error mitigation methods are performing well for long times, and you can compare that with a classical simulations that have converged in those regimes. And then we can look at what happens for the intermediate temperature quench, and that's much harder to simulate with the classical methods. You see that the MPS no longer converges after 8-9 Trotter steps, but you can run this simulation on H2 up to 20 Trotter steps. So again, here you have the error mitigated values for the the dynamics at different trotter steps for the error mitigated total magnetization at every trotter step, and you can observe that you do get these stability region that indicates pre-thermal behavior. We did a lot of work trying to compare against a lot of classical methods. So like three kind of big categories of methods. So on the top you have like various tensor network approaches, including the matrix product state that I was talking about that do break down, and also the PEPS tensor networks that kind of are targeting the 2D lattice architecture. Pauli methods are a series of kind of maybe techniques that are based on stabilizer simulations in a very loose way. They have been used quite recently, to simulate like large-scale experiments, dynamical experiments on quantum computers. But you can see that for this particular experiment, basically all of these different techniques break down. So beyond about 7 trotter steps, then none of these methods show convergence. So basically, the kind of take-home message here is that all of these classical methods that we've tried, and they're sort of state-of-the-art. They've been used to to show that other large-scale experiments can be simulated. For this particular simulation, they fail to converge beyond 6-8 trotter step, whereas the digitized dynamical simulations can run up to 20 trotter steps on the H2. Okay, so that was the kind of first part of the talk. I think we were looking at physics and trying to simulate a physical system with a universal quantum computer. Now, a lot of the techniques that I've talked about that suppress errors for these types of experiments, they can also be adapted to a regime where we want to perform quantum error correction. So, where this is kind of work in preparation, but I won't be focusing about the main topic of this paper, which is developing protocols to benchmark primitives of quantum error correction, but I will be focusing on how the techniques that have enabled the simulations, simulations of physics can also be used in a quantum error correction context. So, we know in order to, have applications where we get kind of quantum advantage, we know that we will need to have quantum error correction or some form, even if it's not full tolerance, but some form of quantum error correction will be needed. And this usually, this is a cartoon sort of what the primitives of such primitives are. So you start off with some logical computation that you want to perform, and then you encode that into multiple physical qubits. So you add in redundancy in your system, and the way you perform gates is, I'm throwing under the hood a lot of things, but you perform gates by applying various entangling operations to all of these kind of larger physical systems. In many cases, to do a universal set of gates, you will need ancillary qubits as well to perform things like T gates and magic state distillation or some other type of method. But the thing that I want to focus on is this next part, which is after you perform encoding, you perform these gates, then you need to measure, you're using the redundancy in the system to get information about the errors that have happened in the system. So you obtain these kind of what's called syndrome data that you can then use to decode, that is to find what kind of find where the errors have occurred and apply appropriate corrections. So this is an active form of correcting errors rather than error mitigation and things that I've talked about previously that happen at the level of post-processing. So here's a very simple example of a decoherence-free subspace where you encode a logical qubit into two physical qubits. It's one of the smallest ones. It has a single stabilizer that is under the action of this operator, so the ZZ. Then your logical space remains invariant, and it can detect bit flips, but it doesn't correct for errors. This type of small systems have been used in a very recent work to see that you can use this to increase the lifetime of a logical qubit in a memory experiment. And in this case, the only thing that you need to know to sort of understand how noise suppression works in quantum error in error-corrected computation, or rather encoded in this case, is that when you perform syndrome measurements, that is, when you want to measure this operator minus ZZ, you do that in a non-destructive way. So you would do it by introducing an oscillocubit and getting a phase kickback, and you get some outcome here that is 0 or 1. Yeah? So a 0 indicates that there was no error has been detected, and 1 would indicate that there has been an error. And in this case, the error is the one that anti-commutes with minus ZZ, so you can only detect bit flips. Now, the idea is that, suppose that you have a Pauli error that occurs in between two rounds of these non-destructive measurements. Now, the key thing is that you of measurements, and furthermore, because the probability of detecting an error only sees the errors that have happened in between measurements, then it's also independent on the input state, the logical input state that you have at the beginning of the computation. So I'm gonna reach the end of my talk by telling you that so this is an experiment that we run using on the H1, so the 20 qubit system. This is an averaged over six logical qubits in this decoherence-free subspace. And you see here that the probability of getting a detector click with the raw data, so we don't do any active any suppression of errors, then you get this uptick in the probability of getting a detector click. And this is not, and the assumptions that go into quantum error correction tell you that you shouldn't be getting this behavior. This can have the consequences of that kind of behavior. Can be that you have a lower error threshold, so you need physical error rates that are much lower than what you would predict that the theory predicts, or it could happen that you don't get a pseudo threshold if you have kind of error noise models that behave in a way that is not unexpected, but if you have strong leakage, strong correlations, that typically tends to have, to pose problems. So in here, in the purple line again, this is a combined strategy of suppressing errors where we apply this Pauli twirl, so inserting Pauli operators and randomizing that, keeping track of all how that changes the mid-circuit measurements as well, and leakage, with the caveat here that leakage is not done by post-selection, but it's done by repeatedly measuring out the qubits. So you insert swaps along the way. So, and on the right side here, though it's a little bit small, but you can also see that Although there was in the raw data, so without any error suppression, there was a bias in when for one of the input states. So here with the kind of a state in an X or Y or Z basis, the computational X, Y, Z, yeah, logical. Whereas if you perform these suppression mechanism, then you know, as you would, you get basically like the assumptions that you want, and that it becomes independent on the input state that you started with. Okay, so so this is a take-home message that you can stabilize rate of detecting errors in repeated rounds of syndrome measurements by using these error suppression techniques. And sort of finally, we've seen that the H2 trapped ion devices are quite versatile. They're capable of computations that challenge classical techniques. That is not to say that classical techniques won't progress themselves, but these, so there's the simulation of physics that I've talked about, the quantum magnetism, but there's also random circuit sampling that also that's appeared last year, and it's also another demonstration of quantum advantage. And although I've only talked about suppressing errors in quantum error corrected circuits, people have done a lot of they're starting to have quantum error corrected demonstrations applied to very small algorithms, like adding 1 + 1 or computing molecular energies in H2, H2 being the H2 molecule rather than H2 device. And also a series of demonstrations of components that are needed for in a full fault-tolerant computation. So yeah, with that, thanks very much for being here. And I don't know where the pizza is, but I can't see any pizzas.
It's outside.
Right, so
I'm just waiting.
Yeah, thanks.
Does anyone have any questions? I wanted to ask, if you go back a slide, so
Yes.
your graph. So the punchline here, okay, I was a bit confused by the punchline here. So are you showing that if you just let something sit idly, the number of errors you're going to detect is going to increase over time?
So this, yeah. So this is, so it's idle, but you keep